In today's video, we have a question which says that a steel pipe with, so the moment we see a pipe here, we are referring to cylindrical geometry, right? So a steel pipe with 50 millimeters outside diameter. So these are outside diameter, 50 millimeters. Is covered with a 6.4 millimeters asbestos insulation. So we have our insulation and then it's 6.4 millimeters with a thermal conductivity. So the thermal conductivity of the asbestos is 0.166 watt per meter Kelvin, followed by a 25 millimeter layer of fiberglass insulation. So we have another layer, 25 millimeters of fiberglass. So these are fiber and these are asbestos. Let's say if this is the center of the pipe, so the pipe will also have inside diameter, right? Because the question wasn't focused on that, that's why I didn't even include it. The pipe wall, so the K of the fiber is 0.0485 watt per meter Kelvin. The pipe wall temperature, so the temperature at the outside, right, is 393 Kelvin, and the outside insulation temperature, which is, so we have a fiber insulation and then the asbestos insulation. But since the question says the outside insulation, so we go for the outside, which is the entire outside. And that will be the fiber, has a temperature of 311 Kelvin. Calculate the interface temperature between the asbestos and the fiberglass. So this is the interface because this is our fiber and this is asbestos. So if we have this temperature, let's call this T1, and then so our T2 here will just be 311, and then we have this. So if we are calling this T0, so we have T0 to be 393 Kelvin. T1 is what we don't know, and then T2 is the outside, which is 311 Kelvin. So we want to find the interface temperature, but then we know that before we can get our interface temperature, we should know the actual heat transfer. And then we can relate the heat transfer from this point to the outside to be the same as that from here to here, right? And that can help us find our T1. So we first have to find our Q. So our Q is equal to 2 pi L change in T overall, all over summation of the resistances. So Q, we don't have knowledge about the length, right? So we can find our heat per length equals 2 pi. So change in T overall, we are looking at this portion to this point, right? So 393 minus 311 all over. Now the heat transfer from this point to this point is by conduction, right? So for cylindrical geometry, we establish length R, right? So now let's evaluate that. So now from this point to this point is our outside, right? So let's call this R1. And then from here to here will be our R2. And then from here to here will be our R3. So we'll learn R2 over R1 all over the K. So now from here to here will give us the K of the asbestos, Ka, plus from this point to this point is also by conduction. So we'll learn R3 over R2 all over. So now the thickness here is K of the fiber. Now let's find our R1, R2, and R3. So our R1 will be our diameter, right? Outside diameter all over 2. And that's 50 millimeters over 2, giving us 25 millimeters. Our R2 will be from this point to this point, right? So first, this is our diameter, right? So our R2 will be R1, need to be from here to here, plus this small thickness, so plus the layer, which is 6.4 millimeters. So that will be 25 plus 6.4, and That will give us 31.4 millimeters. Our R3 will also be, we have this portion. So we need from here to here, right? So if you know from here to here as R2, just add this portion to it. So R3 will be R2 plus the thickness, that was 25 millimeters. And that will give us 31.4 plus 25. And if I'm right, that should be 56.4 millimeters. So now our curl per unit length will be 2 times 3.142 multiplying, so that's our pi, multiplying 393 minus 311 all on ln. So we should have converted the millimeters into meters, but then because we are finding the ratio of radii, we don't need to convert it, they will cancel out. So ln R2 is 31.4 all over R1 is 25, right? So the millimeters will cancel out all over our Ka. That was giving us 0.166 plus ln R3, which is 56.4 over R2, which is 31.4. And that should be all on Kf 0.0485. So our KL per unit length will give us, so evaluating the numerator, 2 times 3.142 multiplying 393 minus 311, and this is 515.288, all divided by, evaluating this portion to ln 31.4 divided by 25 all over 0.166 plus ln 56.4 divided by 31.4 all over 0.0485, and that's giving us 13.449. So our KL per unit length will eventually be 515.288 divided by 13.449, and then we have 38.315 watts per meter. So now the heat transferred from this portion to this portion is giving us the 38.315. But then we want to find our T1, right? So this is our T1. And then we know that when you do the same manipulation and find the heat from this point to this point, you are still going to get our 38.315. So then we will create Q over L should be equal to 2 pi L multiplying, so T1, because T1 will be at higher temperature than T2, minus T2, right? T1 will be at higher temperature than T2 because the inside, this portion has 393 and this has 311. Yes, so this has higher temperature. So the temperature will be decreasing. So at T1, it will be at higher temperature than T2. And then because you are looking at heat transfer from this portion to this portion, it's just by conduction, right? So ln R3 over R2 all over K of the fiber. We know our K per length to be, so we have per length here, so we can get rid of this L. 38.315 should be equal to 2 multiplying 3.142 multiplying T1 minus T2 was 311 all over ln 56.4 divided by 31.4 divided by 0.0485. So 38.315 should be equal to, so 2 times 3.142, that gives us 6.284 multiplying T1 minus 311 all divided by ln 56.4 divided by 31.4 all on 0.0485. That gives us 12.075. So this can multiply this, right? So 38.315 times 12.075 all divided by 6.284 being equal to T1 minus 311. So when we evaluate the left hand side, 38.315 times 12.075 all over 6.284, that gives us 73.62. So we can add our 311 to it to get our T1. Then our T1 becomes 384.624 Kelvin. So now our T1 is 384.62 Kelvin. Yeah, so that is the temperature between the asbestos and then the fiberglass.